So as we mentioned, in the very first lecture, right, a system can be viewed as a process in which input signals, right, triggers some output signal, okay? So a system can be viewed as a process in which input signals are transformed by the system into these outputs, or causes the system to respond with these output signals, okay? So there are a lot of things that can be, considered as systems, right? As we, talked about at the very beginning. But for our engineering or EE, applications, these systems could be, for example, communication systems, right? Where you input a sequence of information that you would like to transmit, right? Then through some encoding and modulation, you output a signal that is suitable for transmission through the channel, right? So this channel could be a wireless channel, or it could be a wireline channel, formed by either coaxial cables or telephone lines, right? Now, another example is, hi-fi systems, right, where you input these low-quality audio signals, and you output signals, right, audio signals of higher quality. All right? Now, you can categorize systems into continuous time and discrete time as well, depending on what is the type of signal in the input and output. So if the input and output are continuous time signals, then you say that the system is continuous time. Right? And if your input and output are discrete time, then you say that your system is a discrete time system. Okay. All right. So systems are, processes that generates output signals in response to input signals. Okay. So we often denote the input and output, of a system with an expression like this. Okay? So we write the input with an arrow to an output signal to denote the fact that y of t is a response to the input x of t of the system. Okay? And similarly for the discrete time case. Okay. Right. So a system is a process that produces output signals in response to input signals. Okay. Now, certainly different systems may produce different outputs in response to certain inputs, okay? So to describe a system, you must be able to characterize what is the relationship between the input and output, okay? So a system is characterized by the relation between its input and output, all right? Okay? So different systems may produce input and output with different relationships. Okay, so in order to characterize these different systems, you need to be able to describe what is the relation between the input and output. Okay. Now let's look at a couple of examples. Okay. So in this example 1.8, we look at a simple circuit system constructed by this RC circuit. Okay. So in this system, we're treating the input as this voltage V sub s of t, and we're treating the output as the voltage across the capacitor V sub c of t. Okay, we treat the input as this voltage of the source, and the output as the voltage across the capacitor. Okay. Now, in order to characterize this system, we want to be able to describe explicitly what is the relationship between the input and the output. Okay. Now, by Ohm's law, we know that the current I of t should be equal to be Vst minus Vct divided by R, right? So the difference between the voltage, right, divided by R characterizes how much is the current flowing through the resistor, okay? Now, we also know that I of t should be equal to C, right? This capacitor here, C, times the derivative of the voltage across the capacitor, okay? So the current flowing into the capacitor, determines the speed of a variation of the voltage. Okay. So this tells us that this is equal to this. Okay. So this gives us a characterization of the relation between the input and output. All right? Now, we're usually more accustomed to writing, the output on the left-hand side and the input on the right-hand side, right? So we know that what kind of output is, generated as a result of the input, okay? So if you sort of move things around, right, moving the output VC, this VC to the left-hand side, and the input VS to the other side, right, we get an equation like this. So we get d VCT dt plus 1 over RC VCT equal to 1 over RC VST. Okay? Right. So this equation here describes the relation between the input and the output, and therefore helps us characterize this system that we're looking at. Okay. Now, in this example on the bottom, right, we're looking at, this vehicle, traveling in this direction, right, due to a force imposed on this vehicle. Okay. So in this vehicle system, we define the input as the force that we impose on the vehicle, right? So F of t, right, is the force that we impose on the vehicle, possibly, by stepping on the gas pedal to move it forward, okay? And the output will be the resulting velocity of the vehicle. So let the output, set the output as the velocity v of t. Okay? All right, so we have a force in this direction. All right, we assume that the vehicle has mass m and that there is friction that is proportional to how fast we are traveling. Okay? So we have a friction of rho vt in this direction. Okay? All right. So we know that the equivalent force imposed on this vehicle is equal to the mass times its acceleration. Okay? So the mass times its acceleration, which is the derivative of the velocity, okay, is equal to the equivalent force, which is F of t minus the friction rho v of t. Okay. So this equation here characterizes the relationship between the input, which is the force, and the output, which is the velocity. Okay? So again, we're accustomed to writing the output on the left-hand side and the input on the right-hand side. So if you sort of move things around, you'll get the derivative of v plus rho over m v of t equal to 1 over m f of t, okay? And this is the equation that characterizes our system. Okay. All right, so these are examples of the continuous time case, but the same follows for the discrete time case as well, okay? So on the next slide, we have a couple of examples of the discrete time case, okay? So in example 1.10, we're looking at the balance of a bank account every month, okay? So the time index here is month, okay? So suppose that xn, the input, is how much money we put into our bank account every month, and yn is the amount of money, right, the balance, right, remaining in our bank account, at the nth month, okay? So suppose that our interest rate is 1%, right, monthly, so that, starting from the balance in the previous month times 1.01 gives us the, basic, balance plus interest, okay, going into the next month, plus the additional money that we saved into it, okay? So this equation characterizes the relation between the input-output of our banking system, okay? So again, we're more accustomed to writing the output on the left-hand side. So we can write this as yn minus 1.01 yn minus 1 equal to xn. Okay? All right. Now, in this example 1.11, right, we're constructing a discrete time system from by sampling from this continuous time system of example 1.9. Okay? And the motivation here is that, if you want to simulate this system in your computer, you can always, you can only, simulate this in discrete time. Okay? So in order to simulate this system in your computer, you must actually sample these signals at integer multiples of certain time interval. Okay. So suppose that we sample the signal at integer multiples of delta, right? And approximate this derivative as the difference between, v of n delta minus v of n minus delta divided by the duration. Okay? So if you do that, right, your sampling will generate these discrete time signals Vn, which is equal to the sample at an integer multiple of delta, right? And a input sequence Fn that is equal to f of n delta. Okay? All right. And then plugging this into this equation here, right? The derivative now is approximated by the difference, okay? It's now approximated by the difference between two consecutive samples divided by the time difference, okay? Plus rho over m, v of t, where t is equal to n delta. Right. So we have plus rho over m, v of n. And then on the right-hand side, we have 1 over m, f of t sampled again at n delta. So I get 1 over m, fn. Okay? Right, so if you sample the continuous time system at integer multiples of delta, this is an equivalent, expression of the relation between the discrete time input and the discrete time output. Okay? Right. So if you like, you can sort of reorganize this to make it cleaner, right? Maybe combining the VNs together. So this will give you Vn minus m over m plus rho delta Vn minus 1 equal to delta m plus rho delta Fn. Okay? So this is just, sort of shifting around the terms to give you something a little bit nicer to see. So these are just examples to show you how to characterize a system through, the relationship between its input and output. Okay? So like we just mentioned, a system, right, is basically a process in which the input signal, right, produces a certain output signal. Okay? So different kinds of systems, gives you different outputs in response to a certain input. Right? So if you are able to characterize what is the relationship between the input and output, you're basically able to, define what this system is that you're looking at. okay? Now, sometimes systems are constructed by a combination or interconnection of multiple subsystems, okay? And you can put together these subsystems in different ways. All right, so there are systems put together through series or cascade interconnections, through parallel interconnections, or a combination of these, okay? So it shouldn't be too difficult to imagine what these things would look like, right? For example, for a system with series interconnection, this could be something like the microphone system we talked about previously. All right, so a microphone system may have a subsystem that converts the audio signal into electrical signals, right? It could be cascaded with a digital signal processor, and then cascaded with an amplifier, and then cascaded with a speaker, okay? Or if you're looking at a communication system, right? So let's say you take an image, right? Image that you take from your camera. You may perform source encoding, right, to compress the image, right? That's one subsystem, right? You may add in some redundancy through error control coding, right? That constructs another system. This encoded bit of information may be converted to a continuous time, EM wave that you transmit through the channel, right? And to do that, you pass it through a third system, okay? So many systems, right, can be viewed as a cascade of multiple subsystems, okay? Now, sometimes this combination may not be in series. Sometimes it may be in parallel, right? Something like this. So for example, if you're looking at a microphone system with two microphones, right, then you can view this as the system of one microphone, this as the system of the second microphone, which you later add together, right? So this could probably help you construct a stereo effect in the final recording, okay? And right, so in general, right, a system can be much more complicated, so you probably have to have different combinations of these interconnections, okay? Right. Now, another common type of interconnection is the feedback interconnection, okay? So in a feedback interconnection, right, you have one system taking an input and producing an output, but you have another system that takes the output of one system and then uses it to determine, to alter the input of this system, okay? And this is often seen in control type systems. So what is an example of a control system? So one thing could be like cruise control. Okay. So in most automobile systems that you see right now, right, you can often switch on cruise control that lets you stay at a steady speed as you travel on the highway, right? So in that cruise control system, right, you can view the input as the force you impose on the vehicle and the output as the velocity, right? Now, in order to stay at a fixed velocity, you might need a feedback interconnection to control the force that you impose on the vehicle, right? So if the velocity becomes too high, you have a feedback interconnection that tells the input to reduce the force. And if the velocity becomes too low, you have a feedback interconnection to tell the input to increase the force, okay? So this type of feedback interconnection is often seen in these control type systems, okay? Now here we have an example of this feedback interconnection in a simple electrical circuit. Okay? So this is a RC circuit, okay, where with a current source, right? So why can this be viewed as a feedback interconnection, right? So suppose that you view this current source as the input to a capacitor system, okay? So then you can draw this input-output like this, right? So you have an input current source, I of t, going to a capacitor system, and you let the voltage across the capacitor be the output, okay? So V of t is the voltage across the capacitor, okay? So this current going into the capacitor charges this capacitor and makes the voltage increase, okay? But as the voltage increases, you will discharge through the resistor, okay? So as the voltage increases, you will discharge through the resistor, causing the actual current going into the capacitor to reduce.